We can start whenever you like.
Yeah.
Okay.
Let's
control.
Since probably I don't know how long we are able to use the Zoom platform, but let's get started in case of time. All right. Well, hello all. Thank you for coming. I would like to thank Professor Serkant and Çetin for accepting to be here today, delivering this very interesting seminar for us. Let me read one of his short bios here before getting started. Professor Serkant Çetin graduated from Boğaziçi University. I think, am I right? Both MS and PhD degrees are gotten from
That's
University in 1996, 1998, and 2002, respectively. He started his faculty position at Doğuş University in 2004 as associate professor, and served as Vice Dean at the Faculty of Arts and Sciences in the years between 2006 and 2009. He promoted to professor position in 2009, acted as Vice Rector between 2009 and 2011, and founded the Department of Physics in 2011 at that university, I guess, right?
That's right.
Having joined Istanbul Bilgi University in September 2015, he founded the High Energy Physics Research Center in March 2016, of which he is still the director there. He served as Vice Rector between 2017 and 2018, and the Dean of the Faculty of Engineering and Natural Sciences between 2018 and 2019. His initiatives on gathering the National Experimental Particle Physics Community resulted in the establishment of the General Board and Representatives Board. In 2016, he was elected as the Representatives Board Chair. He was nominated as the representative of Turkey within RICFA. What is the open version? I don't know.
That's Restricted European Committee for Future Accelerators. It's an international scientific advisory board.
Okay, very good. Okay, and you were the organized by the RICFA country visit to Turkey in 2017. Yeah, he serves as the national contract for Atlas and CAST experiments of CERN, as well as for best 3 experiment of, there are so many acronyms here, I don't have any idea.
It's a collaboration taking place in China.
In China, okay. He acted as the university representative and deputy director of the Turkish Accelerator Center project. He received TFD Professor Şevket Erk Young Scientist in 2004, TÜBA Distinguished Young Scientist in 2008, and TFD Professor Engin Arık Scientist 2015, and TFD Honor Awards in 2017. Well, congratulations, so many successes. Yeah, I mean, well, I'm very happy to be here today.
Thanks greatly.
To hear this work. Well, thank you so much again for being here and for delivering such an interesting seminar today. Well, thank you.
Thanks a lot for this introduction. It's really my pleasure to address to you things that I am excited about, and I also enjoy sharing what I'm excited about. So if I may start, I should just first say that my talk will have 2 different parts. In the first part, I will briefly talk about what CERN is and what we do there, what kind of a place that is. It will be like a teaser in a way. It's impossible to really even summarize all the programs and research that is carried out at CERN. And in the second part, I will talk about what good does this do to us as mankind, to humanity. Where do we see the reflections of such research in our daily lives? To mention those. Hence the title in general is what's happening at CERN and what does it trigger for the society? Me as a physicist, I'm going to try to talk about these issues. Okay, yeah. So here you see that what we are doing is kind of like a travel in time, in the sense that we do today some preparations, experiments to understand or carry out experiments in the future. And we do these experiments in the future that we prepare today, let's say, to understand the past. So there is such a weird relation of time, since we physicists see time also only as another dimension added to space. This sounds normal to us. But this very much looks like the famous movie in the 80s, I guess it was, Back to the Future. Are we doing such a thing? Well, in the sense that I explained just a minute ago, yes. But of course, this is like a joke. The real answer is no, we are not traveling in time. But we are looking back in time. We are looking back in time to understand the current conditions of the universe. To understand today, we need to know about past. So if this were a social sciences seminar, I would be talking about the necessity of history. Information on history is important in living today and designing the future. And this is what we physically do as well. So my point of view is always such that sciences in general, no matter if it's fundamental sciences, physics, mathematics, or engineering sciences, or social sciences, a scientific view always kind of embeds this idea. Now, in this evolution of the universe cartoon, you see on the left-hand side today, and at the very right-hand side, the beginning, where we are today. The universe is about 13.7 billion years old. And at the bottom of this left figure, you see the average temperature of the universe. It's minus 270 degrees Celsius. I'm not going to go through this cartoon. I'm sure you're already scanning through it, different places, because time runs crazy there. I mean, life started like 10 billion years after the Big Bang. However, solar system was formed like 9 billion years later, the Big Bang. And however, after 200 million years, the stars and galaxies were already formed. And about 400,000 years later, after the Big Bang, light atoms were already found. However, it took only 3 minutes after the Big Bang for the light nuclei to be formed, to be created. However, the nuclei, which embeds the protons and the neutrons, as you very well know, these ingredients, protons and neutrons, were already formed hundreds of a millisecond after the Big Bang. Now, why I'm going through this time scale is the following. You see a very light gray bar, a column towards the right, expanding actually vertically. This is like 10 to the minus 25 seconds or 10 to the minus 20 seconds after the Big Bang. And this is kind of the place that we are looking at through experiments at CERN. So we are, as I said, trying to understand the past, but when I say the past, it's not like a linear scale. We have to dig in very, very small pieces, and you can only go like 10 to the minus 25 seconds close to Big Bang, not to that instant. How are we doing this? This is like a controlled experiment that we all learned during primary school, what the definition of a controlled experiment was. We just create the conditions of such an environment and do experiments, and then take data and analyze what we observe to understand what might have happened at these conditions in the early universe. I'm going to go in details to that. Sorry, this was like a zoomed view of where we are really searching. Hence, as I said before, the comments here actually just summarize what I've mentioned. We try to understand what happened in the early universe to understand the origin of the universe. However, the experiments that we have to do for this is not easy stuff. It's not something like you make a plan and then make a demo run, etc. in weeks, in months or so, even not a year. It takes tens of years, it takes decades to really design and prepare these experiments. And these things we do actually to understand something like 14 billion years ago, right? And even if we start to build up something, to design something today, it will take like a quarter of a century to realize those experiments. These are very, very big stuff. But what is our purpose really? What matters to us in these experiments? Why do we do these? Well, there are two actually basic questions we want to answer. One of them is to understand the nature of matter. And second, to understand how this matter interacts with each other. Okay? So understanding the structure, what it is, and then understanding how that structure interacts with its environment. This is very normal. This is, again, I will make the reflection to social sciences, be it psychology or sociology. You first identify the items, the entities, know their structure, their mass, their height, etc. And then you also have to know how does that person act to that person, how does he behave to the other one, how that society gets relations with another society. Hence, this is what I say by understanding matter, like the individual in social sciences, and understand how it interacts with its environment, like the relations that an individual would build up one-on-one or as a group in society. To do that, of course, we're not performing social experiments. We are doing a physics experiment. We need some instruments actually to prepare the conditions that we want to analyze. And these instruments are not things that you can go to the market and buy on the shelf. These are called particle accelerators because we want to give these particles very, very high energies as if they were living in an era that is almost the instant of the Big Bang, very close to those times. Hence, in that condition, particles would have huge energies. But normally, on Earth now, our daily lives, we are not dealing with such huge energetic particles. Hence, we have to make them energetic by hand. And the instrument to do that is a particle accelerator. It's like a particle kicker, so to say. Another thing that I'm going to mention is the detectors that we have to also build, because after these particles gain the energy and interact with each other, we want to see what is happening. And it's only possible, not by eye, but with detectors that detect the outcomes of these interactions. As I said before, these are not technologies or products that you can buy on shelf. Hence, even the current technology does not, as is, let us build these instruments. We actually force technology to the edge to really attain the instruments that we require for these experiments. Hence, there is a two-loop interaction between what we do as fundamental scientists and how this pushes technology. The first one I already mentioned. We are requiring such on-the-edge technologies that it doesn't exist, and we push industry, we push technology to develop what we want with the, of course, whatever ingredients that technology and industry has at the moment. Second, after we do those experiments and analyze our data and learn more about the structure of the universe, then we gain knowledge, more knowledge about the universe. And this knowledge is not something that we are after as physicists, as fundamental scientists, to know and then to turn it into technology. No, that's not our purpose. We are not applied scientists in that sense. But having put this knowledge to literature, then the applied scientists and engineers in future use that knowledge to really create, build up, or innovate new technologies. That has always been the case, and that will always be the case as well. Okay, when I talk about particles, I should mention fundamental particles, or in other words, building blocks of the universe. What do I mean by fundamental? I mean that these are particles that do not have any inside structure. They are not complex particles. They don't have ingredients. They are the smallest entities that we can deal with. However, as you know, for example, the atom is not such a particle. It has electrons in it, it has the nucleus in it, and nucleus has protons and neutrons in it, etc. However, when the structure of the atom was actually on the menu, it was thought to be the smallest particle, right? We all learned during our secondary or primary school years that even the dictionary definition of atom in Latin is the smallest and unbreakable, etc. That is not true today. That's like a joke. However, it was true for the time that information, that knowledge was gained. Hence, we respect history and keep the name atom as it is. But today, those fundamental particles are other stuff. Even the proton and the neutron are not fundamental. They or even have ingredients. So we search for such questions. We try to give answers to those questions. And those questions are like in 4 items, like what is matter made of is the first one. How do we classify these particles? As you know, classification is always to rule to do any scientific research. And third, what are their properties? And fourth, last but not least, how they interact. Well, doing this, as you might have guessed, we are always trying to look to a smaller and smaller and smaller scale. But how small? Of course, it's not mathematics that we are doing. It's not. It's not something that you can infinitely many divide into, like in mathematics you can. But the physical world is not working like that. So we are searching for the fundamentals. Second, I said, how do we classify? Well, classification was done in the history of humanity. It was always a problem, like the fire, like soil, like air, right? And you have these 4 stones, for example, representing that classification from the Fifth Element movie, which I liked a lot. And in Turkish, there is the joke by Cem Yılmaz, as you know, the 5th element is tahta. However, it's like a joke today, but it was the truth. It was what we knew by that time, and it was a very good classification. Today's classification is, of course, much different. And with that classification, we also understand the properties of these particles in order to make correlations between them and also make mathematical modeling of the structure and interactions of these particles. The last item was how they interact. And I find this example that has just shown up very good to explain this. For example, you can create anything from 2 strings, right? You can make a cardigan, you can make, I don't know, plover, you can just make socks, or if your head is cold, you can make the hat and put it on. Please pay attention to the fact that whichever you are actually producing, you are making the same operation with kind of 2 one-dimensional objects, let's say this, the strings. You kind of merge them into each other to make a node, right? Hence, if I would zoom onto that hat there in the picture, nobody would be able to differentiate the nodes that you see, whether it was the hat, whether it was the sock, or a cardigan, a pullover, a shirt, etc. This example I give in order to emphasize the importance of interactions, understanding interactions, because once you understand the nature of the interaction, then you are able to give answers to a wide variety of flavors that you see in the universe. Okay? It's like playing with Lego blocks. We want to understand what the basic blocks are, and second, how each individual Lego block interacts with each other to make a secondary structure, right? If we understand that, we can then understand a very complicated picture. So we can backtrace its ingredients towards what they are and how they interacted to make up, that made up this complex structure in the end. And this complex structure, you can just make the analogy like the universe. So understanding the universe relies on understanding the basic building blocks of the universe and how these basic building blocks interact with each other. Okay, so it's like trying to decode how this wall was made. So when I say fundamental particles, it's like the bricks that you see there. Each are fundamental particles. However, even to make this wall, if you just put the bricks on top of each other, it would not be a stable wall, as you can imagine. Hence, you have to put something in between, right? Without putting the cement in between, you will not make a durable structure. So this cement, putting the cement inside, is analogous to understanding the interactions of the particles, like each brick is interacting with each other through the cement. Okay? So we are doing a simple job. And these are things already I tried to explain. And I also mentioned that we are doing such things at CERN, but what is CERN? Well, the mission of CERN has 4 parts. The first one is research. So we ask the stupid and crazy questions about the universe, and we try to find the answers to those, and we do. Second is technology, the relation I tried to explain already. It's a twofold relation. First is forcing today's technology to the edge. The second is throughout the knowledge that we gain from experiments, tomorrow's technologies are actually built. Only then engineers and applied scientists can visualize or project what they can build up with that information. The third one, and very, very important one, is collaboration. This is such a wide collaboration of science over the globe. And CERN is a unique interdisciplinary, wide collaborative structure. It's the biggest such collaborative structure existing in the world, in any discipline actually. And last but not least is education, that any student would have through his graduate years by taking role in these collaborations is also a unique opportunity. About history of CERN, in '52 actually, the European Council for Nuclear Research was founded. I don't speak French. The first one is Conseil Européen pour la Recherche Nucléaire, which builds up the acronym CERN actually. Normally it's in Turkish especially thought of as a center. The C stands for center, but it does not. It's like, it's for the council, because there was a council formed. And the question was, after the World War and etc., how can Europe actually get its strength back? And the answer was discovered to be found in scientific international collaboration. And this is why this council was formed. And in 2 years' time, the council finalized its preparations and made the proposal to all countries, and turned the council into an organization to be able to take international action. Well, there were 12 founding members from Europe that built up CERN as an organization. As you very well know, we, Turkey, also feel like we belong in Europe, so we want to also be part of the European Union for many years, etc. And this actually is not only for today, but it was also then. So you can imagine that Turkey was part, however, it was not. We were not part of the founding organization members. Maybe we don't want to spend too much time and effort and also money for such international efforts. However, today, the number of full members to CERN is 23, and some things change in Turkey as well, believe it or not. So the number increased, and Turkey always wanted to be part, as I say. And we look at the list, no, Turkey is not part again. So as I said, some things change, but some things don't. There are some associate members to CERN, and the number is 7. Turkey is among the associate members with the very well developed other countries, as you know. And we became associate member in year 2015, although we applied for full membership in 2009. In 2 years' time, 2.5 years' time, Turkey withdrew her application for full membership. It was a strange story, which I never got to get the details of. And finally, in 2015, we were only an associate member. And there are also some observers. Turkey was actually an observer state of CERN since 1961. It was the first observer status given when it was ratified in the CERN Council that such a status could be named. Turkey applied for it. And when associate membership status was officialized, Turkey was again the first to become the associate member, although we aimed for the full membership. So you see also these observer states like the US, the Japan, an institute from Russia, the Federation of Russia, European Commission, and UNESCO. And in addition to that, almost 40 countries, with 40 countries, there are memorandum of understandings, and about 20 countries have other various scientific contacts. So in total, CERN is an organization, a complex organization, that embeds more than 12,000 people not working or not employed by CERN, but registered to CERN. Just like myself, I'm not a CERN employee. I am a user of CERN. I'm a registered user of CERN. And there are such people, thousands of people, more than 12,000, as I said, from all over the world, from more than 600 institutes. Well, as I said, explained before, in order to understand the nature of particles, we need to give them high energies and then make them collide. A collision is also a joke, and it's a lie, by the way. Nothing collides. Even when you hit your hand, it's not a collision as we understand. It's an electromagnetic interactions that the electrons outside the surface apply to each other. Hence, there's an electric force, so to say, and this force turns into pressure force per area, and we just feel it in our brain like a touching feeling, right? Sense. The particles, they don't collide like colliding balls. They come in close interaction. They come to very, very close spatial coordinates. They are very close, and they are high energetic, and they start to interact with each other, just like our hands would interact when we hit our hands to each other. However, as I said, to understand what's happening there, we need to build around detectors, because it's not visible by eye. Even if it were, we would not catch what's happening, because it happens at a very, 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 very small instant of time, okay? Very small period of time. Now we do such experiments and we discover some things, and well, sometimes people get also the Nobel Prize for it, just like the Higgs discovery that was made in year 2012, and a year later the Nobel Prize was given to the discovery, and because of the discovery, to the proposal like half a century ago of this Higgs particle by two theoreticians, the pictures of which you see on top, and at the bottom picture you see the crowd that is enjoying the announcement of the discovery at CERN. However, as I said, in order to do that, we need to accelerate particles. But what are accelerators? They are simple stuff. We all know that like electric charges repel each other, and opposite charges attract each other, right? So if you have a proton, let's say, just like the one you see on this cartoon, red ball, then it would move from left to right, from the positive to negative voltage plates, right? And that's an accelerator, simply. But of course, it's a complicated stuff because you need to oscillate this field, the electric field, in radio frequency in order to give a push to the proton all the time. And we accelerate these particles to energies that are otherwise not attainable with these instruments. And then you make an interaction. What you see here as a cylinder is a typical description of a particle detector. By the way, such a thing is not a small thing. Consider this cylinder to have a diameter of 20 meters and a length of more than 45 meters. And this system to be placed 100 meters underground. And when a proton comes from the right and another one coming from the left collide at the center, then because of the interactions, many different particles arise, and we need to know what is coming out of that interaction, and this is what our detectors do. And again, I repeat, these detectors are not also on-the-shelf technologies. We do design them, and we force the industry to be able to be capable of producing such things, and the industry benefits a lot from this because this is an R&D for them, otherwise which they would not even imagine why or how to do. And then using that R&D and know-how that they have gained, they use it to produce other goods to sell, of course, to the society. Okay. So far so good. I'm going to leave for a minute for you to watch how the Atlas experiment was built 100 meters underground. And this is one of the experiments that appeared, that exists on the collider that I mentioned, which collides the protons. Each part was lowered underground, one by one, and then put together. It took years to first design, to make prototypes, and then produce at different places on Earth, then bring to CERN in Geneva, in Switzerland, and then bring together 100 meters underground. The reason that you see many, many different parts is because we are interested in finding out different characteristics of different particles. And this requires that our detectors are built with different technologies. Some parts only detect, for example, position. Some parts only detect the energy. Some parts are put there to divert their path in order to calculate their momentum and figure out also whether they're a plus or minus charge carrier, etc. And our ultimate goal from that information we gain is to identify what particles came out and what their properties were. We read about millions of electronic channels at each collision, and each collision happens, and then another one happens in 25 nanoseconds. So in a second, it's like 4 million crossover of proton bunches, and each crossover contains like 20 to 50 interactions. So it's a huge amount of data that we have to handle, and I'm going to come back to this big data handling in my second part of the talk. Now that you have seen our detector built, by the way, it was built really, and it's working since 2009. Now we go to the accelerator tunnel, 100 meters underground. Now we are a proton, and 3 quarks inside the proton are very excited because they are high energetic. They approach the center of our detector, Atlas detector, from one side and the other side. And at the heart of the detector, they will interact. The quarks and the interacting particles of the quarks, which are called gluons, will produce new particles that we want to observe in our detector, as you see in the animation, like tracks or depositions of energies. Of course, such a mass means nothing. You have to analyze this mass to get something out of it. And these analysis algorithms are not again things. It's not only instrumentation that's not on the shelf. It's also the software. It's also the algorithms. And it's also the methodology and techniques that you should apply for data analysis. They are not on the shelf. We do invent and prepare those frameworks. And those frameworks later on, again, take their places that serve humanity in a sense. I show you here a real data analysis result, which resulted in the discovery of the Higgs. That is what was the Nobel Prize given for. Because of this discovery, these 2 gentlemen received. The colored histograms and the data points, if you do check, that they most of the time agree with each other, but towards between 100 and 150 on the x-axis, which is the mass, you see something weird and you say, well, there's not agreement. Is there maybe another particle, Higgs particle maybe? Then we add to our simulation, if there was a Higgs, how would it behave at that mass? And now I repeat again the animation so that you can take a look with that view. And in the end, we see where there was a bump. In other words, disagreement between our known theories and what we observed, and whether this disagreement could be explained by the existence of a new particle, Higgs particle, we implement in the simulation. Well, it seems that, yes, it gives such a bump, and it actually matches with in a statistical significant way, the observed data results. About the history of this collider, the Large Hadron Collider, it was, as an idea, brought up in mid-70s. Okay? Towards the end of 80s, there was an alternative idea in the United States to build such a high energy proton collider, which was called super collider. However, it was canceled in about 5 years. And also the efforts and the money from the US was channeled to CERN to proceed with the Large Hadron Collider in Europe. And that was 94 when LHC was approved by the CERN Council. And in 97, experiments to take place, the detectors to take place on the collider was approved. And in 2005, we had the projection to start. However, there were delays. It took like 3-4 more years to really do everything. And by 2010, we were able to get data. And the data that you showed on the previous slide was accumulated in 2 years. So the discovery of Higgs was through the runs that were taken in year 2010 and 2011, and some portion of it was displayed on this screen. And is it okay? We did find Higgs, the missing particle. What is Higgs important for? Because it is the answer to how fundamental particles gained mass. That was a missing point in our theories. We didn't find such. So our model to understand particles may seem to be now complete, but it is not. The more we know about the universe, the more information we get about the universe, the more we also learn about our inconsistencies in the theories. Hence, we know that there is much more to what we thought describes everything as a very good and global model, which we call standard model. And today, we know that there should be much more to it. As an analogy, I can give you the following example. Consider the Newtonian times. Newton mechanics, some of the people you might hear saying, some physicists saying that Newton mechanics was wrong. Well, the answer is not an easy answer to give like that. Newton mechanics was correct for the conditions of the dynamics and the actions that were analyzed. Yes, it was correct, but for subatomic particles, it didn't work out, okay? Quantum mechanics ruled over. So consider quantum mechanics like a global set and Newtonian mechanics as a subset of this theory. And actually, very nicely, the mathematical formulation enables to take limits, and you can get, for example, from quantum mechanic equations, Newton equations, if you take the speed close to zero, or if you make the dimensions large, etc. But these are details. Why I'm saying this is because of the following. There is a lot to know more, and we know that we don't know many things again. And this experiment is not something that you design and do the other day or year. Once it's built, it's only built for once, and it's only built at a unique place like CERN, because many countries join their forces in that effort. Hence, we need to get the most out of this machine. We need to get most of the information that we can get with it. So we have to have a lot of data to dig, because data does not tell you right away, here I am, I'm Higgs particle, please discover me. You just have to dig in a lot of dirt, so to say. Hence, LHC has a calendar until year 2040, a summary of which is given in the plot you see. Even what will be the next scenario, what after 2040s, what is the world going to deal with as an instrument to collide more energetic particles in a more dense manner, to have more statistics at a given unit time. Well, that is even questioned starting from year 2010. And the future circular collider is now being designed in its design stage. By design, I'm not talking about final design. It's just proposal design stages. Once it's finalized, it will be built like prototypes, etc., and then it will take place. So we are talking about like 25 years later at least from today. So in parallel, the community of particle physics all over the world is dealing with that as well. I just wanted to give you an, as I said, teaser, an idea about what our excitation is and why we are doing these experiments, the goals to understand the universe. And in my second part, so I should now, apologies, switch to another screen and change slides. Could anyone confirm whether you see my new slides?
Yes, we can see.
Yes,
the full screen view, not the PowerPoint program itself.
That's the new presentation.
Okay, great. Now I'm going to talk about something that I'm not personally involved in, but I am very much interested and trying to stimulate society and decision makers and governments to show interest. How can fundamental science, fundamental research trigger industrial applications? What are the examples around us? This is what I'm going to talk about. So fundamental science is like the startup, then you have applied research, and then you have product development. It's always a chain as such. always with the start of a fundamental question, which triggers an applied science or research, which results in product development. This is like beacons of discovery. It's a name that's given to our field, the products of our field worldwide, and I like to use it a lot. This is why I showed the header page of such a site actually, but which was in Turkish, Beacons of Discovery. If you search for it, you can find it. Google. Well, we ask many different questions, and or better to say, in our daily lives, we just face up with many different things like the drugs, the pharmaceutics that we have to take for health, for transportation, cars, or IT technologies, many things. Okay? And all of these things we don't know, but for them to be developed as efficient and let's say adaptive to our needs as possible, relies on accelerator technologies and detector technologies. Okay? So there are many highlights that you can read, which I'm not going to do. The English version you can find on Google when you click Beacons of Discoveries. But what I like a lot is the fourth item, which says, I can go from 1 to 1,000, but I need help to go from 0 to 1. So going from 0 to 1 is the fundamental research. Going from 1 to 1,000 is the applied sciences and engineering. And it's an ecosystem. There is no such thing as, yeah, let's only take the 1 to 1,000 part and be successful, as unfortunately our decision makers think works. But it's together with the 0 to 1 part, because this is where you get the manpower also educated around. This is why I say it's an ecosystem. And this is the unique way that you can have a fundamental scientist working hand in hand with an applied scientist and or an engineer. Okay? Otherwise, there is no such things. Otherwise, our engineers and applied scientists only duplicate or only work on known technologies and try to develop them. They cannot, because they don't interact with fundamental scientists on this vision, they cannot build up their own innovative approaches or new ideas. There are many examples where particle accelerators and detectors are applied. Like in figure 8, you see an image of the brain that is only possible to take with such detail with a PET scanner, as you most of you very well know. PET is a positron emission tomography device, where the used device consists of particle detectors. Okay, they detect photons that come out of the tissue, and the reason that happens is because the patient is given a radioactive, which has a radioactive element which has very small lifetime, and it then triggers some interactions in the tissue, and then it emits photons that the detectors detect, and this is how you get a film of your brain or any other part of your body. However, that small lifetime radioisotopes are not existing in nature as they are. They are only artificially produced. And guess where they are produced? They are only produced in particle accelerator systems. When you bombard, let's say, an oxygen atom, it can only turn to that kind of a radioisotope. You see in number 9, for example, the statute, which refers to archaeological, let's say, findings or understanding historical findings without destructing them. It's only possible through particle detectors that you take tomographies of such valuable findings. Even before they are found, it's possible to scan the Earth with these tomographic detector devices. I already mentioned that we are forcing the technology to its edge. Hence, it's an important interaction of a physicist, engineer, and technical personnel. Otherwise, what we do at CERN would not be possible. By the way, it's about 10 times more people that are employed by CERN who are engineers and technicians. It's only 1/10 of that community, which is physicists. This is also a good number, I guess, to show the importance of how engineers and applied scientists are important in our endeavor as well. Well, I'm just going to give some keywords. There's no, it's not possible in the given time to dig into details of these technologies, but one of the keywords is like cryogenics. Cryogenics is important in order to operate systems that have superconducting technology. Well, superconductors, as you might have heard, are conductors that do not have any resistance to a current, which is incredibly good, right? You don't lose any energy when you send an electric current. But there is one withdraw, that this conductor, superconductor, does not behave as such in room temperature. It only behaves as such under very, 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 very low temperatures. For example, the superconducting material that is used at the LHC and also at parts of the Atlas experiments are only active at minus 271 point something, I forgot, degrees Celsius. So only just a few degrees more than the absolute zero temperature in Kelvin, right? So it's not possible with your fridge to obtain such a low temperature. Hence, this is very, very advanced technologies, and this is where the future today and the future is. Well, furthermore, it's not only the superconductivity that is needed, but you see some cavities in these pictures. And as you can imagine, we do accelerate and collide protons, but they are not going in pipes that have like air and other gases. It should be vacuum, as you can imagine. And the vacuum level should be very, very high. Ultra vacuums we are talking about. A vacuum such that you have even less pressure than the pressure between the planets in the in our system, okay, in our planetary system. So it's both high vacuum technologies and ultra low temperature technologies that are important. And these have extremely many application areas in industry. Well, we know about the very sexy word innovation. It's one of the, actually, since it's a new kind of a concept that is in our lives, I did mention the mission of CERN as research, science, collaboration, and education, but the fifth one is innovation. Well, it comes, how to say, provided that you have the four, the fifth one comes free. It's a natural outcome, but only with that ecosystem. This is what I'm trying to mention. This is why CERN has actually innovated such many things. Even the reason that we are able to really communicate with each other over remote conferencing systems over the web, etc., is because web was invented, the World Wide Web was invented in '91 at CERN, which is not widely known. Many other inventions took place at CERN. Such inventions feed the industry, then the industry is able to produce more and stronger tools to carry out fundamental research. So such kind of dual relation between fundamental and applied sciences exists. And I emphasize again the importance of such ecosystem. Well, what kind of technologies I'm talking about? I'm just going to name them. You can read them later on. I can give you the slides if you want to post somewhere as a PDF. Well, detector technologies. It has incredibly many application fields. IT technologies, A very good example is the discovery of the World Wide Web. Today we are talking about computation on grid, right? You're just submitting a job somewhere, you don't know where it runs, and then you just get the answer. That was also invented because of the needs of the big data we have to analyze at CERN in these experiments. All these systems, the platform, the frameworks, they at least become a question, and then there are solutions, and then we experience it, we use it, and then it finds places worldwide where they are applied. Accelerator technologies. It's not only for us to accelerate these particles to understand better the nature of the universe, but these accelerators are used in places that you cannot, or sometimes even I cannot imagine. Some of these examples I will give later on. Some solid examples would then be the following. Detectors, it's like trying to see the universe, the whole universe through a needle, right? Through the pin of a needle. So Atlas detector, in this eye, it's a superposition of an image by the Atlas detector, collisions taking place at the center. There are, let me try to remember, more than 10 different types of technologies used as detected technologies, and millions of electronic channels, as I said, and all is to understand what was happening there. But then, these detectors are used in many different areas, like security, like medical sciences, like understanding the nature, the structure of material in material sciences, etc. For example, nano is also another sexy word that we use in our daily lives. Nanotechnologies, nanosciences. Well, there would not be such a keyword today if there were not any accelerators invented on Earth. Because the reason we were able to understand and analyze materials in that scale was because of the synchrotron radiation that you can only obtain through particle accelerators. That's a unique opportunity. That's why, and this is like a triggering block. It triggers many different, also fundamental and or applied sciences when you apply. So these I'm going to be faster because I think I'm running out of time. It's been 3, but we started like 10 to 15 minutes late. So we have different types of detectors that found applications in different areas. An example of which on the left is given. Such kind of a detector called XPAT was used in actually computer tomography systems, okay? And the firm invented this PIC-SCAN tool that actually bettered the usage of PETs, so positron emission tomography systems, and there's a much better 3D understanding of whatever is being analyzed through these detectors. And you can see how many pixels it even has with respect to what is shown here as a stick, very, very small micron size pixeling I'm talking about. Well, IT technologies, as I said, www was formed there. The father, even the grandfather of most remote conferencing systems, one of them, Zoom, we are using, was developed at CERN. It was called EVO. And CERN used EVO, and then it just open source served to the community. And then these things built up like Skype or whatever you can name or imagine. Even conferencing tools, you can search the web for Indico. It's a free software also invented by CERN to ease preparation of organizations from smallest meetings to biggest size conferences where, I don't know, maybe 3,000 people attend with hundreds of different fields and parallel sessions. The grid technologies I already mentioned, and also the software that is developed, because it's not on the shelf, as I said, because nobody ever made it as a need or addressed it as a need. We have important software developed by the particle physics community that do simulate how particles interact with matter, how radiation progresses in matter. And this has, you can imagine, again, many applications. And also the framework where data can be analyzed, which we call root, is an important development that is in C++ and Python. And this is actually when and where the very famous nowadays scripting language Python was actually born and known by many users. Okay, I already mentioned root. I already mentioned the World Wide Web, its relation to economy. I think I don't need to mention the world lives on the web today, right? No other word is needed to say. I can even relate it easily to Industry 4.0 because I already mentioned the need of the World Wide Web. Why was it? So many people are active at CERN, but they're not at CERN all the time. And they need access to what is happening real time. They need a real-time monitoring of what's happening and interaction. This triggered an engineer and in IT department to actually introduce the www framework in the protocol under HTTP. And first it was not very much liked by his supervisor, and he said, this is not on our to-do list, so don't spend your time on it. But the guy kept on working, and after a year, it was the world's biggest innovation. And we deal with a lot of data, hence we need data processing at parallel sites. And currently our data processing structure embeds the world like a grid. This is why it's called a grid. And the data that we take is copied to different tiers, to different sites. And then when you want to analyze something, depending on the availability all over the world, your job is just starting somewhere, and maybe it's split into parts. It's just processed in parallel, brought back, merged, and you just see your final output data, which you can then analyze by root or any other software that you have developed yourself. And such a system, not only for analysis, but also in the data acquisition system of the more than 1 million channel detector system, requires an automated system, automated decision chain system, both in software, manipulating electric signals and making maybe different thresholds to take the correct data. And you know that this is what Industry 4.0 in terms of industrial production mechanism chain relies on. This auto control system, automated control and decision making system to make the process more efficient, fluent, less time, whatever you say, less cost, etc. This is already what we do. Not even part of what we do, but this is exactly what we do. Hence, this is why we are today talking about Industry 4.0 as a revolution, as Özgür Hoca was referring to it, which I like a lot. Just to maybe tell you a few more things that you did not know, the touch screen was also invented at CERN. It was in 1973 by this gentleman who was an engineer in the accelerator control room, very much bored of having to change the control panels every time there is a change in the, accelerator system. And he used the capacitive, he invented the capacitive touch screen in order not to have to mechanically change always the control panels, but to be able to program them. The same gentleman, in about the same time, also invented the mouse. Okay, so he wanted to an indicator on the screen that can move in XY coordinates. So he made a billiard ball sit on two cylindrical switches. When you push with your palm and just move, then the indicator on the screen would move to the coordinates that was actually addressed by the hardware. And that's the working principle of a mouse. Later on, as you know, it's in our lives. By the way, when I'm talking about mouse, maybe they are young participants would not understand what I'm talking about, such a motion. But in the old times, what we called mouse was not, of course, an optic mouse. It was a mechanical mouse which embedded such a sphere inside, and which made us crazy from time to time, because when dirt gets in, you don't see your mouse operating smoothly. Hence, accelerators are like the key to 21st century. It all started at early 20th century when Ernest Lawrence first invented the first ever accelerator, for which he got about 10 years later the Nobel Prize. By the way, this accelerator, as you saw in the figure, is something that would fit into your hand. Okay, it only accelerated particles up to 80 kilo electron volts. An electron volt is an energy that any particle with one electron electric charge would gain in a potential difference of 1 volts. Okay, so this is like 80,000 volt energy given to one electron. Today, after 80 years, let's say, or more, sorry, 20 years, but during the time when LHC started, I mentioned, we have a big instrument, Large Hadron Collider. It has a circumference of 27 kilometers. It's a circular shape, as you see, and it's 100 meters underground, and it accelerates protons up to 6.5 tera electron volts. Okay, so look at the development. And it has these applications. These accelerators have many different applications. Processing wires, processing stretch films, rubbers for the automotive industry, even processing ink, such that if you have an ink which is produced that had been processed by electron beams, then the ink actually dries faster, so it's more handy. Okay, and infinitely many, let's say, other areas. Some examples are mentioned here, but I'm going to go very fast. Direct production with electron beams, melting with electron beams, welding with electron beams, electron ovens, name given, reshaping with electron beams. I'm talking about reshaping material with electron beams, and processing with electron beams, lithography as well with electron beams. Well, they can treat cancer cells. You know, the therapy that you go to, radiotherapy, is actually with electron beams. Also, I talked about the ink processing, etc. It can be many other things that it can be applied to. Flue gases in big production plants, power plants. This example I'm going to actually extend a little later on. You can disinfect actually solids, actually sterilize liquids with electron beams. In China and other countries, the city water is actually cleaned up with electron accelerators in a facility and then served back to users again. It does change the polymer structure in cross-bonding structure. Hence, such a change is very, very crucial to have a more durable, strong, long-lasting, not burning, let's say, polymer production. And that's a unique way to be able to do that. It's only with particle accelerators with electron beams. And also sterilization of whatever medical instruments or food, etc. And here I just summarize which energy gap is applied to which fields. It's not important that we go through them right now, but in medical sciences, it's very widely used. And here I only start from Röntgen, as you see the famous picture. Today, we can take the brain picture or any organs of the body in very much detail in 3D. This was just a 2D picture. And this is a patient in a PET tomography instrument. What you see as a circle here is bits and pieces of particle detectors. These are crystal scintillators. They do detect the photons that come out of the patient, and then they are reconstructed as images. And as I said, the reason that the body emits these photons is because of the low half-life radionuclide that is put to the patient, but this is only produced in particle accelerators as well. Well, very, very new thing meaning, I mean, in the last decades, there is also radiotherapy which uses not electrons or gammas, but protons. And what is important is that, as you heard very well, very much over the years, radiotherapy actually triggers other diseases in the well-being of a human, because it kills other healthy tissue on the way. However, if you accelerate protons and fire these protons to the patient, you can have the possibility to tune the proton to give most of its energy to its target only, not on the path. And this is what we call this Bragg peak. This line, as you see, it's not depositing much energy on the way, but it is depositing most of its energy on its target. So this hadron therapy is very expensive. It's in very few places in the world. There are about 50 plus centers that do it worldwide. In Turkey, we don't have one yet. So there are many, many medical applications. And for example, the Atlas experiment has many inputs and benefits to society in terms of culture, in terms of, again, medical applications, other technical applications, which I'm not going to go into detail now and here, but want to mention one important, maybe this will be the one or two of the last ones. By the way, how much time do you think I have? If time is tight, I can just finish up in a minute.
Well, you can. I think you can take.
Okay, maybe 5 more minutes is going to be enough for me. Accelerator-driven systems are very important because this is a new type of nuclear power plant. This is the system technique that is the basis of a new type of nuclear plant. It is not yet realized all over the world, but many designs are going on. Well, you know how power plants work. Well, you need to convert some form of energy into another form of energy, which we call electrical energy, in order to distribute over the network, right? They can be hydroelectric, they can be wind energies, thermoelectric plants, and the conventional nuclear plants, as you know. By the way, no energy source is as powerful as a nuclear plant. Hence, any alternative energy source can only be site productive for the needs of a nation, let's say. So it's always nuclear power plants, and it will always be nuclear power plants that bring up the energy that you need at your home and in general for industry. Well, but there are problems with nuclear plants, as you know, and the world has experienced severe accidents, Chernobyl and then in Japan, etc. Why is that happening? We very well much know, because there's a chain reaction which you cannot stop. And when something happens, radioactivity comes out. Well, instead, so this is the chain reaction. What triggers that chain reaction actually is through a neutron. So you need to bombard the uranium with a neutron, and then whatever happens, happens. If you want to stop this, you have to stop the neutron bombarding. But conventional nuclear plants have like other doped nuclear fuels that send neutrons all the time. Hence, you cannot differentiate the two. You cannot take one out. It's not a process that you can act on. However, if there was a possibility to stop that neutron bombarding of the uranium to the uranium, then you would be fine. And you know what? This is possible with nuclear plants that are driven by accelerators. Hence, imagine a nuclear plant where the neutron source is not another nuclear element, but it is a particle accelerator. Imagine a proton hitting a lead shield, and when a proton hits the lead shield, neutrons come out of it. And these neutrons are used to do what conventional nuclear power plants also do. But the only and very good thing is that when you turn off the switch of the accelerator, then you will stop the protons, then nothing will hit the lead shield and nothing will come out as neutrons from there. Hence, no chain reaction. This is an incredible, let's say, era in terms of energy, new era in terms of energy production. And furthermore, it's not only this that this system is good for. This system, the design of which is shown in the figure here, sorry, is also used in order to make the used nuclear fuels, right, the garbage nuclear, the waste, the nuclear waste, be less radioactive, because the radioactive waste is an important issue of a nuclear plant. You have to seal it and hide it for thousands of years to be safe. However, if you take this nuclear waste and put it in your accelerator-driven system, then it changes the structure and it makes the nuclear waste, it turns it into a form which has much less half-life. Okay, hence then it's not so dangerous. You can only keep it for much less time, not for centuries or thousands of years. This is sometimes a bigger reason that most countries actually are interested in the development of ADS systems. So I talked about sterilization. Here is an example with fruits, where they are used in the world, etc. The flue gas is important. You know, there are plants that use electron beams in their flue gas filtering, because when you bombard the flue gas with electrons, it catalyzes a reaction that is not happening so good within itself normally, and making actually the filtration through a chemical process where, how to say, the product ammonium is produced, and later on you put the standard filters and you get a very clean gas that comes out. And what is important is that what you obtain as a product, because your only need is to make a good filtering, but it's not only a very good filtering, but it also produces something which is an artificial fertilizer that you can use in industry. And this is very valuable. And there are power plants that use this, and they run at zero cost because of the sale of these fertilizers. Okay, they don't spend money. Technologies require, as I said, cryogenics and low vacuum, ultra low vacuums. But you can imagine the accelerator is at minus 270 degrees, and something like half a meter later, you are in room temperature. So how to have a material that actually stands a gradient of 300 degrees Celsius in between almost, right? This material in between for isolation is also unique, and it is developed for these needs. And now it is applied to different places in industry. For example, the Geneva airport is now covered with such isolators, and it is the best isolation that any airport in the world has so far. Because we are associate members, we our companies in Turkey can also go to bids that are happening at CERN, and we can make use of the know-how, and also we can take the information to work on it ourselves. But again, as I said, this requires a very good ecosystem. So my resulting words are more or less summarized throughout my talk, so I'm not going to go over them. It's just a summary of what we should do in Turkey to really reach maybe 2023 goals. The real path to do that was through forming this ecosystem. So this was like an advice to achieve these goals. But my aim in this talk was really to give a glimpse of the relation between fundamental sciences and applied sciences, and how one benefits from the other, and how one would not be living, let's say, would not exist without the other. So they are hand in hand always. Thank you for your attention.
Well, thank you so much, Serkant Hocam. Well, it was really amazing presentation. I wasn't aware of such works about CERN, actually. I'm very surprised, and I'm very excited about hearing such important works, even related with Industry 4.0. I would ask that question to you, but you have already explained how it contributed, the works contributed to Industry 4.0 as well, from an industrial engineering point of view. Well, a lot of works, basic science is really important for us. Once we also notice that again. Thank you so much. I would like to ask participants if whether or not there is any question to direct Professor Serkant Çetin on the issue, on the subject.
If I may just get in for a minute. Hocam, thank you very much for the presentation. I've actually enjoyed it immensely, but I'm going to have to jump to another meeting. So I was going to say, please do excuse me. In a couple of minutes, I have to join something else. And so thank you very much, and hope to see you soon.
Thank you.
Okay, any questions about the subject to Serkant Çetin Hocam? Anybody else?
Well, I may ask Serkant. You know, you already told us about the Higgs boson, but the popular name for the Higgs boson is the God particle. Why do they name it God particle?
It was actually proposed to name it goddamn particle. The reason being that it was proposed theoretically like mid-60s, and the world was burning to find it because it was a very beautiful theory. It did explain the missing part of how mass was given to particles. It was very suitable to the theory that we already thought was working on, etc. But we could never find it. The missing part in the theory, in the proposed Higgs theory, was that the theory is not able to predict the particle's full characteristics, what mass it has, how it interacts, etc. So we need to search a huge phase space to either rule out or discover this particle. Every effort until CERN's discovery was a rule out stage, and the community, the science community in general, the world, was fed up with not being able to find the Higgs. So every time experiments were done, they required more energy to produce more energetic collisions, such that in the end you can create more massive particles. So we always knew that, okay, we need higher energy colliders, and CERN's LHC was the right one to tune up with the mass that is needed. And we were able to find in the end. But how the name was given was in mid-90s, another Nobel Prize winner physicist made a popular book where he explained about the particle physics in general. And he mentioned about Higgs And when at a place where he mentioned about it, he said, the goddamn Higgs particle has not yet been found. And the editor of the book said, we cannot say goddamn particle in such a popular book. It's not blah, blah. But since it's, he made the analogy that it's like generating mass, it's giving mass. So why not omitting the damn and say it God particle? That was very much liked by the society. Well, the physicist, the writer actually didn't want to publish it as such, but he couldn't resist anymore. That is the reason the God particle name was given to that. At different talks or seminars, when people ask me such a question, I also sometimes give the answer, come on, they are all God's particles, so no differentiation. It worked.
Okay.
Okay, so any other questions? So Serkant Hocam, let me ask you about, your work. CERN works related with smart manufacturing or Industry 4.0 related works or collaborations. Is there any work going on with the guys or with the research institutions such as Fraunhofer, some technology producers, technology research centers in Germany or some other countries? Are there any works or collaborations with such research centers or institutes to contribute Industry 4.0 or smart manufacturing environment?
I get the question. Well, the answer to that is both yes and no in the following sense. CERN's mission is not to be involved in how to say, this progress of takes place in the world. For example, CERN is not producing PET devices. CERN is not producing accelerators for sterilization. CERN is pushing the need for the existence of such devices. And then this know-how, when it is distributed to member states, etc., all over Europe, then that country actually takes it as an income. And Germany, as you can imagine, is a very, very big contributor to CERN. And they have a big volume at CERN. And Germany is where Industry 4.0 rose up from. If you would be able to analyze, I'm sure, the different support mechanisms for scientific fundamental sciences and applied sciences in Germany, you would find the relation there, not at CERN, but there, which has this interdisciplinary or handshaking support mechanisms such that such systems are evolved. However, I heard, I don't know frankly, myself directly, about many seminars, many working meetings about Industry 4.0 at CERN as well. So there are groups going and coming and meeting with different departments of CERN in order to be able to get what they need, which they don't know. Because CERN is a unique example where such questions or problems or challenges are faced for the first time. And even that experience in decision-making, in data acquisition, in control mechanisms, etc., are things that CERN experiences only for fundamental research. But it is this methodology that the outside world is missing, is seeking. Hence, they come to get this experience and know-how from CERN. That is kind of the borderline of interacting with industry in that sense.
Right.
So did I understand correctly? So there are the research going on at CERN, the accelerators or the collider at CERN is unique. So everything that accelerator collider requires a unique solution, a customized solution. So everybody working to provide that unique technology also gets some byproducts, which will be then adapted in our daily life or daily needs. Is that?
That is right. Yeah, that is right. But I just wanted to specify how that happens. What I want to say is the following. If I was employed by CERN and if I was an accelerator physicist or an engineer in that department, I would have no action item given to me by my supervisor to work with an outside industry firm to develop an accelerator for hadron therapy for them. They come to CERN employees and groups, understand the details, the techniques, and then they develop themselves. CERN is not an industrial application development center. It doesn't have this mission. It's not defined. It's ruled out actually. However, the very important relation is the following. Let's say that I did my PhD at CERN in an accelerator division. I produced some simulations and then did some demo testing, made some productions, put them in the test beam, etc. I graduated. I did a postdoc maybe at another department. Then I don't want to continue in fundamental scientists. I want to continue in applied scientists. I moved to that firm. And these firms all around the world actually seek graduates of CERN. It's not an institute, of course, it's not graduating, but different universities, the students work at CERN for their PhDs, and a majority of PhDs that are attained from CERN programs go into industry. And the ratio is, I think, something like 1 to 7 or 1 to 8. This is an important bonding with also the environment. I have a very close friend who did his PhD in Boğaziçi. I was in his thesis jury as well. He worked at CERN for a while and then he is now a key engineer in an engineering department, a key physicist, which acts like an engineer because he moved to applied sciences in a hadron therapy development company.
Okay. I have another question. We might have some undergraduate students among our audience. Well, are there any, you mentioned about data analysis, statistics, and things going on like that at CERN. Do you think that there are some opportunities at CERN for industrial engineering students for their internship, for example?
Definitely. Well, we had even one example from Bilgi University. One of our industry engineering program students was accepted to CERN summer school for about 3 months, and half of it was a mandatory, in a way, internship scale project that she had to deliver. So it's not only electronic engineering, computer engineering, mechanical engineering or mechatronics engineering or software engineering, but it's also civil engineering, industrial engineering, believe it or not, bioengineering in it. That we have all the disciplines embedded in because there's a need and link to each other. And the answer is yes. There are summer schools at CERN that everybody can apply, and there are also internship positions at CERN that, of course, there are open calls. I mean, that's, for example, period. Maybe there is no need for an industrial engineer, but it does happen. It does update itself quite often. And I also try to motivate and trigger my students to apply for CERN internship positions.
Okay, thank you. One final question from myself, and then so other people may ask other questions. But I'm also interested in your opinion about the education system. Okay, we are maintaining an engineering program, and we are industrial engineers. We are teaching industrial engineering. Sometimes we have the discussion of whether we should have some fundamental science courses in our curriculum, like physics, chemistry, and so on. And you know, at the first glance, you know, we don't have any kind of direct usage of chemistry or physics in our curriculum. What do you think about that? Why should we have fundamental science courses in our curriculum? What do you think on that?
Well, it's not only you, but even social scientists should have physics courses. It's unfortunate that a common understanding of physics is very solid, something you can hold in your hand, break, make in balance, or rotate. This is physics. This is physics, but this is also physics. This touch screen invented at Cern, for example, I gave the example. However, the important notion about whether it being turning or touch screen is that physics is the unique place in the history of mankind where one asks questions about a case and tries to find answers that he can convince others as well by repetition of the same scenario. So physics is the reason why calculus was invented. Otherwise, any engineer would not be able to do any integration or derivation.
It would also contribute to
the following point.
I guess. Sorry for that, but I just wanted to add, it would also contribute to entrepreneurship kind of thing, right?
Exactly, very clear. So it's not important that a student learns net force is equal to mass A. It's important to get that student understand that net force is equal to mass times acceleration is a relation that is valid in nature, and mankind was able to find out this relation because he bothered to ask himself, well, how does that fall? How does that move? I guess, be it engineering or any other, be it industrial or any other discipline of engineering, it's always about asking questions, trying to find answers in a mathematically modeled way, and then making a product that can work out for society. Even if it's a software engineer or an industrial engineer, I don't believe it is any different. Hence, physics is like an intermediate stage which actually trains one's mind analytically to observe first, observation, get data, understand data, make a meaningful outcome from the data, make a proposal, and then check whether it fits with your observation, your proposed mechanism. And if it is yes, then put it to the market, understand it, explain it to people, and convince them to use it as well. Can you now tell me, was I a physicist explaining this or was I an engineer? You would not. So this is why physics is in the basis of analytic approach, observation to data, data to making getting some meaning out of it, and then that meaning, that modeling, cross-check with the observation. If it works, then put it on the shelf. This approach is For engineering students in the first year in physics courses, it's like a very, very important training of the mind, because they do deal with things that are in their daily lives. They observe apples falling all the time. They observe wind breaking the window all the time. They observe light all the time. They do work with electricity all the time, computing, etc. Everything that they are putting their hands or feeling is related to the very simple physics laws that they learn there. And if they get during that time this understanding of how this relationship, how this reasoning has worked out, most students would even, I have at least some students that merged from physics, from engineering to physics after really enjoying this understanding. I get your point that you are not using physics directly in your product, but this is like we are using a language to communicate, but we are physicists or engineers. So it's physics is like, well, mathematics is the tool of physics. And then it was applied to economics, social sciences, industry in many ways. But physics is the tool of engineering. And this tool, you don't have to be a mechanical engineer only, electrical engineer, or computer engineer. As you said, even industrial engineer, it's always the same thing. Observe data, make a meaning out of it, model, and then put it back to observation, match, cross-check, modify, etc. This whole process is an engineering process that was built by the physics science in all times.
Thank you.
So to
Yes,
extend your
so
question,
much.
I really but truly believe that not only engineering and science students, but social science students should get basic notions of fundamental sciences such as physics and chemistry. I know such interested people, students or graduates, when they are interested and when they have some knowledge, they have a much more open mind, and not only openness, but their skill set and capacity to actually elaborate on issues is much more different than a standard educated social scientist. This is a real difference.
Well, thank you so much for the explanation. Yeah, I totally agree with you. Personally, I totally agree with you. Fundamental science is really important for any engineering discipline, especially physics. As in, for instance, medical schools in abroad, especially in United States, without completing biology, 4-year biology education, they don't go with medical school. Something like that. So we should think about our curriculum actually as engineering faculties. We should rethink on the novel developments, and in my opinion, we should also consider including so many math courses for engineering curriculums as well. All right, we have actually limited time, almost 13 minutes is left. Automatically it's going to be closed. I mean, the system will be over, platform will be closed. So if there's any other questions, please direct it to Serkant Hoca. Otherwise, I'm going to say thank you. Thank you to him for joining us, for delivering such an amazing seminar for us. Hope to see you again, hope to meet you again in the future with some other subjects. Thank you again.
Next time will be face-to-face, something face-to-face.
Yeah, hopefully, yes.
Yeah,
Thank you, Serkant Hoca, for keeping it in English also. Thank you very much. It was an amazing presentation, very interesting.
Yes,
okay,
thank you.
Thanks a lot,
Thank you, take
so
care.
it was my pleasure. I thank for the invitation again, and yes, really hoping to meet you face-to-face in the near future, I hope.
Bye.
Bye-bye.